So after cleaning up the board a little bit, we find that we have an expression here for an arbitrary approximation of the area under the curve. And what I mean by that is I can choose any number for n that I want and allowing it to percolate through the function we have, we ultimately end up with some expression for the area under the curve. Now, part of what we notice is, regardless of what n value we choose, we always have this error under the curve. We use the rectangles to approximate the area, but no matter how many rectangles we make, we're always going to end up with that weird little chunk at the top of each rectangle that's, in our case here, underestimating our area. Well, what are we going to do about that? Well, if you recall from Calculus 1, we had a similar problem. When we were going to find the slope tangent to a function, we started off with a very poor approximation. We took 2 points and we brought them closer and closer to each other. We evaluated the limit as those 2 points get closer and closer to each other, and that brought the error in the slope infinitesimally close to 0. Well, we can try that here as well. Now, we want to be a little bit careful with what term we're going to be limiting here. We have 2 potential candidates here. One potential candidate that we might be really motivated to check out is this n value. In this case here, if we take n and make it infinitely large, that makes an infinite number of rectangles, each of which has an infinitesimally small error. If we take the limit as n goes to infinity, this will create an expression whose area is a perfect representation of the area under the curve. When we evaluate the limit and make n go to infinity, this will force an expression whose error in approximating the area under the curve will be infinitely small, therefore will be a perfect representation of the area under the curve. So why is there another, I don't know, 5-10 minutes to this video? What more is there to do? Well, it turns out another way we can think about finding this perfect area under the curve, another way that we can limit this function is, rather than saying that n goes to infinity, if we think about how n is equal to the width of the entire area divided by the width of a particular area, we see here that we can also think about changing delta x itself. Furthermore, if we take that delta x and we shrink it down, make it infinitely small, in response, the number of rectangles that have that width blows up. We can fit more tiny rectangles in that width as we make those rectangles tinier and tinier. So another way then to find the area under this curve is to say we will take the limit as delta x goes to 0. In doing this, we are controlling the width of these particular rectangles, and by making those shrink down to 0, we then force the error for each individual rectangle to go to 0, and therefore we have the perfect area under the curve. And here we have an expression of an infinite sum with an infinitesimally small value. We have an infinite sum of an infinite number of infinitesimally small rectangles that add up to the total area under the curve. Okay, so I've rewritten our perfect approximation of the area under the curve. I've rewritten it so it looks a little less horrible and with bad handwriting. My apologies to colorblind individuals. I also rewrote it with some different colors so that we can kind of easily see where different pieces kind of slot into the function. And all of this was to show this expression I have written here is a giant pain to write. It's a nightmare. It's a giant nightmare. When I sit down to solve a calculus problem, I don't want to get bogged down in this weird notation. Believe me, as we get into more advanced problems, there's going to be plenty more other notation. I don't want to have to write this stupid sum thing every single time I write a problem. What can we do to deal with this? We're motivated then to come up with some sort of notation that condenses a lot of this information down in such a way that is easier for us to interpret. Something we can do here is something very similar that we might have done when we thought about evaluating the derivative and when we came up with more condensed notation for that. We understand in the back of our mind when we do the derivative, we have this limiting process in there. When we do the difference quotient, we understand we have that limit that helps us condense down our 2 points to make our perfect slope. But when we do the dy over dx notation, a lot of that information is wrapped up in there. We can do something similar with this. We can come up with a piece of notation whose entire purpose is to condense down the limit for us. In addition to that, we're going to write down something that not only takes in the limit, but eats that sum up as well. It becomes important for us to understand that we're taking a sum. So we're going to write something down that acknowledges those two pieces at the same time. And that thing is this funky S. Oh, yes. In reality, we have this. We have this funky symbol here. This is called the integral. It looks like a very elongated S, and the entire purpose of this symbol is to demonstrate to us that we are taking the sum of a bunch of terms all at once. Big funky S for a sum. It also tells us that we are taking this limit. We're taking a sum of an infinite number of rectangles. That is the purpose of this symbol. So this symbol tells us essentially that we're doing this stuff altogether. Very important piece of information that we kind of skirted around, didn't really talk about that much. We need to talk about how we define the bounds of our area under the curve. When we think about our function, we specified that we're starting from x equals a to x equals b, and it was arbitrary, random. It didn't really matter what they are. But when we sit down to do this problem, knowing what a and b are becomes important. We use it over here. When we want to know what our delta x is, we have to think about b and a. And in a more general sense, when we're sitting down thinking about the area under the curve, I would like to know, where is my area? Am I taking this area between these two places, or am I finding the area between these two places? Or am I finding the area from here to somewhere over there? Where are we finding the area? This motivates us to think about explicitly what is A and B. This motivates us to acknowledge what those boundaries are. And this is how we do that then. On our integral, we write down what is our lower boundary and what is our upper boundary. The value at the bottom of the funky S tells us our lower bound, and the value at the top of our funky S tells us our upper bound. Okay, so we've acknowledged A and B. Great. Now we need to start filling in the actual function. We may be motivated to simply drag and drop this thing down here. But this is a little complicated. First off, part of our motivation for doing this whole thing in the first place was to get rid of a lot of these extra symbols that are floating around and making my brain slowly go insane. But also because a lot of the information written inside this function are bound up with the properties of the limit and the sum, which we're trying to get rid of in the first place. One of the ways we can think about this is these values, a minus delta x times I. That tells us where we are in the integral. Depending on how many delta x steps we are, it tells us that we are at a different location within our integral. We step forward 1, 2, 3, 4, 5, 10, a billion times. Well, we're past the point of adding up individual numbers. By taking this limit, by evaluating the limit as delta x goes to 0, we're creating a scenario where we have infinite rectangles. So how relevant is it for us to think about, I'm on step 39 of infinite steps, or I'm on step 400 quadrillion 376 billion 512 out of infinite steps? It's not relevant to us. It no longer becomes important for us to keep track of where we are in our steps. We're not doing that part anymore. And so rather than forcing all of this extra notation inside our function to track that position, we can simply acknowledge that we are doing some operation on f of x. And so all we have to do is we just replace all of that nightmare nonsense with f of x. Okay, we're almost done. We've almost kind of translated this upper bound function with this newer, sleeker thing, expression, function, notation, whatever. The last part is this, that delta x, we need that here. When we sat down to talk about this at the beginning, I was motivated to get rid of as much notation as possible. That's part of the point here. We're trying to simplify this down. But it turns out that delta x is still very important for a couple of reasons. One, we have to remember, yes, they're infinitesimally small. Yes, it's a weird approximation thing, but we're still adding up a bunch of rectangles. And rectangles have two dimensions, length and width. It becomes important for us to remember we have two dimensions that we're multiplying together. When we look at our curve, the areas of these rectangles are given by two pieces. The height is given by f of x in some capacity, depending on where we are in the curve. And the width is given by delta x. So we need to acknowledge that delta x to really maintain the idea that we have an area. We have a two-dimensional object, and we're finding that. But we also have this limit to consider. We have to think about the fact that our delta x is becoming infinitesimally small. Whereas before, when we were not doing the limit, delta x was some number. It could be really small, it could be 1 or 0.1 or 0.000000001, but it was some finite value, some number you can plug into your calculator. No longer. By doing this limit, we're taking the numberness away from it. We're compressing it down into an infinitesimally small number. We're turning it into something that lives within the boundaries of infinity, not numbers. It becomes important to acknowledge that infinitesimality, or whatever the heck it is. Instead of writing delta x down, you may be familiar with this notation. We're going to write down dx. This acknowledges that we have a width. Our rectangles have some width, a dx width, but that dx is infinitesimally small. And this signals to us, especially if we're familiar with differential notation, like we talked about with derivatives, this signals to us that we are dealing with the realm of differentials. We're dealing with the realm of infinitesimally small pieces. This signals calculus. So, congratulations, we've done it. We've created a new expression. We've created a new piece of notation that takes this entire giant nightmare expression of this infinite sum with this limiting term and condensed it down into a nice, neat, condensed little expression. Now we just got to figure out how the heck are we going to use it.